You know, the search for alien life, it's one of the biggest adventures we've ever been on. But really, it's more like a giant cosmic detective story. The clues? They're scattered all over the solar system. But the biggest clue of all, the one that could crack the whole case, might be hiding in our own backyard, in the mystery of how life started right here on Earth.
So, are we even looking in the right places? I mean, it's not just about building bigger telescopes or fancier rovers. The real trick is knowing what to look for. It's about figuring out where the most likely birthplace for life would be. It's forensics on a planetary scale.
And let me tell you, the stakes are massive. We're talking billions, billions with a B on these missions. We're sending our best robotic explorers out there, and these aren't just sightseeing trips. No way. You should think of them as highly targeted investigations, each one chasing down a very specific lead.
So who's in our lineup of suspects? Well, you've got the usual characters, dusty old Mars, the icy ocean moons, Europa and Enceladus, and even the seriously weird Titan with its methane lakes. But here's the twist. The way we choose to investigate each of these places all comes down to a huge scientific debate about our own origin story.
Right, so if we want to find life out there, we first need to figure out how it happened here. We need a recipe, And that's the core of it. Scientists are currently arguing over two totally different recipes for life. The fancy science word for this is abiogenesis. All it means is the process of life popping up from non-living stuff, like simple chemicals. It's the jump from just chemistry to actual biology. It's that initial spark. And figuring out that spark, that's the key to everything.
And this is where it gets really cool. These two competing ideas about how life started here on Earth, they're basically our blueprints. They give us two different pictures of what a nursery for life should look like. And that tells us where to aim our rockets. Okay, so let's look at the two big ideas. First, you have this submarine vent theory. This one says life's building blocks were literally cooked up from scratch, deep under the ocean, using geothermal energy. But then you have the hot spring theory. This one's different. It argues the building blocks were delivered from space by meteorites and then assembled on land in these little wet-dry cycles. So, see the difference? One's about making the ingredients, the other is about assembling them. All right, let's put these two theories in the ring. Head to head, is the cradle of life a deep-sea pressure cooker, or is it more like a primordial splash pool on some ancient volcanic island? Because the answer completely changes our game plan for finding life elsewhere. This table lays it all out perfectly. For the submarine vents, you're on the deep ocean floor. The magic ingredient is the chemical gradients there. And the organic molecules, they're made right on site. The big hurdle, though, is trying to get complex molecules to form in all that water. Now, for hot springs, we're talking about volcanic land. The key process is this constant wet-dry cycling. The organic stuff is delivered from space, and the main challenge is, well, surviving all the meteorites and radiation on the surface. Two very different scenarios.
Okay, recipe number 1, the deep sea pressure cooker. Here's how it works. Step 1, synthesize. Deep sea vents use chemical reactions to create the basic organic building blocks. Step 2, concentrate. The tiny pores in the vent chimneys act like filters, trapping and concentrating these molecules. Step 3, polymerize. The mineral surfaces inside those pores act like a catalyst, linking the simple molecules into complex chains or polymers. And finally, step 4, encapsulate. The unique chemistry of the water helps form little bubbles or membranes around these chains, creating the first protocells. Boom.
All right, now for recipe number 2, the primordial splash pool. Totally different approach. Step 1. Delivery. Instead of making the ingredients, they're delivered from space via meteorites. Step 2, concentrate. Little hot spring pools on land fill up and then dry out, over and over. When the water evaporates, it leaves behind a concentrated film of these organic molecules. Step 3, polymerize. In that dry phase, the molecules are forced together, forming long chains. And finally, step 4, encapsulate. When the pool fills up with water again, these new polymers get wrapped up in little bubbles or vesicles, a completely different process. Okay, so we've got these two very different recipes for life. So what? How does this actually help us? Well, it gives us a roadmap. It literally tells us what to look for when we get to another planet or moon. It's our exploration guide. And first on that map is Mars. And Mars is so interesting because it's the one place in the solar system that could have worked for both recipes. Yeah, ancient Mars seems to have had both deep oceans and volcanic land, making it the perfect place to test both theories.
And get this, we actually have evidence for both. For the deep-sea vent idea, we've got a place called the Iridania region. Data from orbit suggests it was an ancient sea with huge hydrothermal deposits on the seafloor, a perfect spot. But then for the hot spring idea, you've got the Columbia Hills, where the Spirit rover literally found silica deposits that look just like what you'd find in a hot spring on Earth today. Mars, you guys, it might have had both. But then we move out to the icy moons, places like Europa and Enceladus, and the picture changes completely. These worlds are basically giant oceans covered in a thick shell of ice. There's no land, no atmosphere to speak of, no wet-dry cycles. For them, it's submarine vents or bust. It's the only game in town. But that leads to a huge question, a really big problem, actually. For life as we know it, you need certain key elements, like phosphorus. Here on Earth, we get a lot of that from rocks on land weathering into the ocean. So what happens on a world with no land? Could Europa's ocean be missing a key ingredient? Is it a beautiful, habitable ocean that just can't make life? So this is basically the scorecard. For Mars, it's a contender for both the vents and hot spring hypotheses. Yes and yes. But for Europa and Enceladus, it's a yes for vents, but a hard no for hot springs. And this thinking goes beyond our solar system. If we find exoplanets that are nothing but ocean, they might be out of the running if life needs land to get started. It's a huge deal for where we decide to look next. So, what's next on the agenda? Well, this is the exciting part. We are literally about to turn the entire solar system into a laboratory to put these two ideas to the test. A whole new wave of missions is gearing up to do just that. We've got some incredible missions on the case. NASA's Europa Clipper is going to do flybys of Europa to check if its ocean really has the right stuff for the vent recipe. Then you've got Dragonfly. This is so cool. It's basically a nuclear-powered drone that's going to fly around on Titan to study its weird organic chemistry. And of course, there's ESA's JUICE mission, which will take a super close look at the hidden oceans of Jupiter's other moons. We're going hunting for answers. And the results we get back won't just tell us if, say, Europa is a good place for life. The data could actually help us solve the mystery of our own origins. By seeing which of these environments has the right stuff, we might finally figure out which recipe for life is the correct one. And that leaves us with a really mind-bending thought to wrap this up. Just imagine this for a second. We go all the way to Europa, we find its ocean is warm, it's full of energy, it has all the right chemicals, but it's totally, completely lifeless. What would that mean? It could be the most powerful clue we've ever found. It might tell us that while oceans are great at supporting life, they just can't start it. It would suggest that a warm little pond on a rocky bit of land isn't just one possibility. It might be the only way the story of life can ever begin.